Hello there. How are you? Good?
Yes.
Did you have a good lunch? Yeah. And now ready for your lunch, after lunch dip here or not? So sit back and relax, right? Okay, I'm going to talk about the Lambda architecture and with a little bit of IoT use case, which is serving as an example. I am Bas. I work at ING. I realized that we're in Belgium here, in Brussels, where ING is not very popular at the moment. But I'll skip over that part if you let me. So, we're going to talk about the Internet of Things. Well, what kind of things are there in the Internet of Things? Well, you can start with, the promise is that everything gets connected, right, in the Internet of Things. You probably have heard a lot about it or maybe read something. Everything gets connected because devices and hardware will become so cheap that it will actually be only costing a few cents extra to connect something to the Internet. Now it's only maybe cars and big other things, but it will be your fridge, your water cooker, your coffee machine, anything that you can think of is connected to the Internet. Combine it with all the data we already have from other sensors, like the mobile phones that we have, the wearables, the watches, and we have a huge, enormous new big thing called the Internet of Everything, or the Internet of Things. But is there something actually? Is there something new then? What's happening there? Is it like a revolution, something that we did not have before yet? Well, actually, not really. I think it's more like a hyped term that is like denouncing some business opportunities there, which is nice actually, because we have had a lot of technical revolutions. We have had Hadoop and Spark, big data, fast data kind of things. And now Internet of Things is like a more business-centered revolution. You can think of that, large organizations are really thinking about how can we connect things and how can we make use of all the data that is coming out of that Internet of Things. But it does offer a lot of new opportunities and challenges, of course. For example, we have more data sources to connect, so that means bigger data sets. We have new data. We have new use cases, so we have to combine data. New technology, because we have to act on real time to all the data. And last but not least, some new security challenges. What should we secure? What should we encrypt? Should we do it on a network level? Should we secure the sensors or only data on the back end? All those challenges are really where the organizations that are dealing with this kind of problems are dealing with at the moment. So, what do we want in such an Internet of Things kind of scenario? Well, as I also already mentioned, it would be very nice to combine fast data and big data. And fast data is, a term that denounces streaming events, or event-sourced data. And basically, this is also nothing new, because in any kind of streaming environment that you would have, the stream is probably not enough for you to act on, right? You always have some kind of static data source on the back end, because an event is only a very small piece of data. It's only, a person logging in, or a GPS location, or maybe another tiny bit of data. And that is, maybe useful. You can store it, or you can visualize it, but it's becoming really useful if you combine it to static data that is not real time, but is actually being loaded every day or every hour or something in a database. So that combination makes it very, very, very useful to do. And it would be nice if we can have that not in separate systems, like one system for our events, one system for batches, etc., but one analytical engine where we can share data and share code. And also it would be really nice, of course, to have it in one visualization tool, right? We don't want to have business users have to combine them in two separate tools on the front end. And since we are dealing with massive amounts of data, we want everything to be scalable, and we want every piece of software to be reactive, according to the reactive manifesto. People have already read that, maybe. So it has to be resilient, it has to be responsive, it has to be message-driven, because then, we know that the system is responding anyway. Even though the backend systems are maybe failing, events are not coming in as fast as we would like, but our front end, our user interface is responding very fast anyway. So, in comes the Lambda architecture. This is a picture already several years old, of 2013, designed by a guy named Nathan Mars. He worked at Twitter. And he was actually one of the first who thought conceptually about these kind of problems. How can we combine batch and streaming data? So basically, it's a very simple diagram. You have two layers, a batch layer and a speed layer. They both do different things, but they act on the same data. So we have new data coming in, and that will be distributed. And of course, in Nathan Mars's use case, it was Twitter feeds. And we store them in a master data set to be queried in the same way that we do with all kinds of batch data. And in a speed layer, which is effectively, and this time was a Apache Storm cluster. And then on the front end, we have opportunities to query the data, to visualize it, because we are actually selecting data from two kinds of storage layers, you could call them. The technology behind this was typically Hadoop combined with Apache Storm. And it worked, it still works quite well, but it also has some challenges. And there's been some criticism about this. Because Lambda is, it's a conceptual reference architecture, you call them, but it's also, it's quite complex, because you have to keep the data in sync, right? You still have two systems to process the data. You have map, reduce, Hadoop, and Storm to act on the same level of data, and two storage mechanisms as well. Again, map, reduce, and maybe a NoSQL database, for example. And at the end you can combine those two, but then your querying part, your visualization part, will become quite complex actually, because how can you combine those when you're all doing it right at the end? Also, some other criticism was there that it was, for example, it was not really well documented, and the architecture principles were okay, but how should we do it? How is it working in practice? So it's been evolving, and now all other new terms have been popping up. The Gamma architecture, the Kappa architecture, the Omegal architecture. That's three that I heard in the last few months, actually. I don't really care. A lot of people just still call it Lambda. Lambda is actually the broad combination of combining batch and streaming data into one system and acting and making able to act on those. Another step further is that in those kind of modern architectures, we also we don't want to combine those two layers, batch and speed, right at the end. But we want to combine them earlier, because that gives us an opportunity to share more data and more code, right? So what you will read and heard a lot about, and also today at the Spark Summit, is that the difference between batch and streaming is disappearing slightly. Why don't we treat every batch that comes in as a stream of data, right? Because every record in our big data set can also be considered an event. One piece of a stream. Or you can turn it around and you could say, why don't we treat every stream as a series of mini batches? And that's the original Spark method, of course, that was designed in that way. So, and so we have a batch coming in. It doesn't matter. A batch can be a big data set of, several terabytes of data that gets loaded into your analytical engine. Or it can be a very small mini batch of maybe a few pieces of data that has been, that were gathered on your Kafka cluster in the last 500 milliseconds, for example. But then from that point on, your code and your data will be the same. So that's also very useful to think about it in that way. Okay. And I have to mention this because I am in front of a big audience. I have to do some promotion for myself. So this is something that I wrote myself as a reference architecture already 3 years ago. So that was so clever. It was amazing actually. So, but this actually is a standardized model also, a little bit of scientific because it's made with Archimate, like an architectural design tool. And it also has all these kind of principles in it already that says, doesn't matter what kind of data you have, big data or streaming data, we have one reference architecture to process it all. So very nice. Nobody ever did anything with this, but maybe now you will. Right? You're my new hope for the future, so to say. Okay, I want to give an example of this because, that's also what I noticed myself. Lots of these information. At ING we also want to do this kind of thing. We want to combine batch and streaming data. But then you have, if you read the internet, you have books about it. You have lots of presentations and how you call that, blog posts about it. But not really something that says, okay, this is practical way down to do it. You should write this code and then it's all working. So that was a bit of my goal today, to show a little bit of that to you and to have it more, make it for you more practical how you can approach such a problem. I have a sample use case for it, but of course you can take any other use case that you have in your own organization as a replacement for this. My use case is smart parking. Also an interesting topic for fast data and for Lambda architecture. What I would like to do is when I drive into town, into Amsterdam, to get a real-time prediction what is for me the best way, the best place to park my car. Based on, of course, what is the availability of all the car parks. But in Amsterdam, all the car parks are almost always nearly full, especially when there's events happening and stuff like that. So that's not the only piece of data that I'm interested in. I'm also interested in like real-time data, our streaming data, that is giving me information about the cars which are in the neighborhood of certain car parks, for example. Because then you can get a prediction out of that. Says, okay, if there's a car park in the south of Amsterdam and it has a capacity still left of maybe 100 places, but in the neighborhood there's also driving 200 cars in the neighborhood right now, live at this moment. But if you drive 5 minutes further, then there's a car park which has only also have 100 places left, but there's only 50 cars driving around that area. Then I would go for the second one because, it can be very obvious that the first one will be, shut down with cars in a few minutes. So, an example, and what we want to show to an end user who is actually looking at a smartphone while he's driving into town. We want to give him a prediction. Okay, that's the best way to park your car, based on. Two data streams again. Obviously the fast data, the streaming data is the real-time GPS locations of all the cars that are in the neighborhood. We could get them from the mobile phones of people, we could get them from TomTom devices, or maybe the cars themselves, if they are all connected to the internet in a few months' time, so to say. But we also want to combine it with more static data, more batch data, which is actually the data that is supplied by the car park themselves, because they have updates like this one. This is a website of the Amsterdam government that says this is an update that is provided every minute on a web page that says, okay, if you want to park one of these in one of these locations, this is the capacity that's left for that. So we can probably query this with an API and get a data set from this every minute, and then have a batch feed of that coming into our system as well, which provides us useful information, how many spaces are free, but also maybe other factors are important for you. What is the price of the car park, for example? Maybe you also want to know how far is it away from me. That's obviously a very valid choice as well. So that is all, you could say, it's static data. It's not changing on a millisecond basis, but it's changing every minute or every hour, so to say. And this is a visual representation of that. So you could imagine that those blue blocks are the car parks, and the green dots are the cars that are driving around in this area. So if I'm now coming from the south, what is the best car park for me? Well, it's probably not this one, but it's maybe one of the bottom ones, for example. Okay, how do we approach this procedurally? If I get a stream of data, let us start with the stream. The stream of data that comes in, which is the real-time events. First, I have to collect them, of course. In my technology example, I would have a Kafka bus that will be the source of all the events. And every event is a GPS location of one car. So one car is now in this coordinate. Another car is that coordinate. And how many times do we get that? Yeah, it depends on the backend system. Maybe some cars can get an update of their position every millisecond. Some can get an update maybe every second. We don't know, but we don't care actually, because we can link them to unique cars based on their IP address, for example. So we know where the cars are moving and how they are distributed across Amsterdam. Then we should probably be filtering them, because if we gather all the data from all the TomTom devices, then it would be a mess. We only are interested in a subset of the data, for example, only the area of cars that are in Amsterdam. So applying a filter to those events seems very good to limit it down a little bit. We probably also want to store them for several reasons, because we want to look them up maybe in real time. And the storing can be done in memory, or it can be done on a database. But also we want to store the events to be able to replay scenarios in the future and to train our prediction algorithm. So if we can actually build up a very nice set of events that are happening, we can train our own models back on that data again later. So we store them, and then we are going to look at all the car parks again. So remember this picture. For every car park, we're going to determine if that one event that comes in, that one car location, is relevant to re-score, re-rank that car park in terms of the efficiency or relevancy that this is for me. So what I do then is I will combine the batch with the static data. The batch with the real-time data. My batch data and you could say my backend data is called a feature set. And why is that? Because we're doing machine learning. So it's just a name for a set of data that is there on your backend cluster. And that contains all the static data from my car park. So in our example again, that's the price of the car park, the location, that is the capacity, etc., etc. We combine it with the event that just comes in, and we actually what we want to do is to create a running sum, which is called, so maybe a sliding window of the time series that have been happening for the last, let's say, second or maybe 5 seconds. We should be tuning that. And how do you do that? We actually are going to calculate the distance of each car, of each event, to that car park. Have that all combined and summed up, then you have a good overview of how many cars are near that single car park. Yeah? Does it make sense? I see a lot of people already a bit confused, but we'll get to the code in a minute, don't worry. And then we have a feature set ready to be scored, because then we have static data from the backend systems. We know where the car park is, we know its usage, we know its capacity, combined with the real-time data that says, hey, so many cars are now in the neighborhood of the car park, and then we can assign a new score to that car park. Like this is a good car park to park or not. And the score will be a score from 0 to 1, and we can score it with, for example, a logistic regression algorithm. Or maybe you can think of another machine learning algorithm. That's up to the data scientists to decide. So that's our stream coming in. We also have a batch coming in, because we want to update that feature set, which is actually, that's the core of your system, the feature set. We also want to update it from the data that comes in from the government and from the car parks themselves. And actually it's quite a similar process, only we're not doing it for every event. We're not going to re-rank all the car parks, but we just get a list of car parks, a static data set, and we just update the features in the database. And that's what's happening here. But the mechanism itself is the same. Only the first time you loop across the events, and the second time you loop across the car parks. So the benefit of this is you can share the same, for example, domain, you can share the same business classes, you can even share the same scoring algorithms, because in a sense, if you have a new feature set coming in out of a batch, it's probably wise to rescore and reprioritize actually all the car parks based on the new static data that comes in. So that's also the last step. We also predict a new score based on a machine learning algorithm and store that one in the database again to be created by our users and to determine the relevancy of all the car parks in the Amsterdam area. All right, I'm going to. I have a very big timer here, constantly in my view. So it's 10 minutes left, I'll say. So I'm going to speed up a little bit in this part. But this is an essential picture because this is the typical architecture that we're going to use for that. We're going to step away from the process a little bit and look at the technology, which is probably what we're here for. And you see a little bit of the Lambda architecture coming back again, which was in the Nathan Mars's picture, right? We have a batch coming in right on here on the top with capacity updates or another updates from the car parks, and we want to combine it with the GPS real-time updates from the cars in a stream. Both of them are coming into our analytical engine, and we actually going to apply these 3 steps in that based on any type of data that comes in, right? And at the end, we produce a new score that gets, and the score is actually, you know, the score from 0 to 1, determining how relevant and how useful it is to drive to that car park. And that can be queried by an API and published to a front end like a mobile app to the users. On the top, you also see that there's a business rules environment here. I'm not going to talk too much about that, but what you can imagine that business users probably want to have some kind of selection mechanisms that says, okay, that's all nice, you know, your prediction engine is all very nice, but I am actually I want to have some control over it, so I want to have my filter be configurable, for example. So in some cases, I'm only interested in the Amsterdam area, some cases other cities. That kind of filters are coming from your business rules environment. And on the bottom, we have a data science environment, your learning engine, so to say, which is actually producing a machine learning model that is integrated in your analytical engine. And your data science environment is where the data scientists are working on, and they are producing those models. So they are actually working on, again, the feature set and all the data that we've been gathering so far to come up with the best model possible for predicting the scores of all the car parks that we have. And the technology that we use for it, well, it's sometimes called the SMAC stack, or Mac stack, or other things as well. But in this case, we choose some modern technology, not Hadoop MapReduce and Apache Storm anymore. But we chose HDFS. That's still there. The Kafka message broker system, Apache Spark for both the learning environment, the data science environment, and for the analytical engine, for the streaming and batch combination. And we have a Cassandra database to store all the events and the features and the scores. Let's start with the message broker. We're going to look at some code now. How does this look like in practice? Well, actually, yeah, I limited it down because I want it to be readable. So hopefully it's a bit. You don't think, okay, is this all? Well, it's not everything that there is actually, but the actual code is on GitHub. So if you want to look at the solution and have it actually working on your local machine, just get it and you'll see the entire package of this. But for a stream, all the steps that I just told you about are in here. So in Spark, we start with building up a streaming context. In this case, with a batch interval of 1 second. We have a connection to Kafka. And for Kafka, Kafka works with topics, if you know that. So we're only interested in the topics that says that is car data, that GPS data. And we obviously have to connect to a certain URL to have the connection up and running. If you see, I put all the import statements here on purpose because Kafka works with versions, and it depends a lot if you're working with Kafka 08, 09, or 010. There's actually separate libraries for that are there to be used. I used the Kafka 010, the latest one for this one. And then we connect to a stream, and then on this moment we have a stream of what you call raw data events coming in. So actually, in only 3 lines of code, we have a Spark stream up and running, connected to a Kafka bus, and connected to each other. Okay, Next step is to get the features and to apply the business rules. We just continue with our Spark streaming solutions. Remember, we have to stream. What will be first step that you actually want to do is not to work on the raw data, because your raw data is, yeah, what is it? It's probably JSON, or it's maybe even something worse, like bytecode, or yeah, who can think of it, or maybe a string that's containing all your raw data. So in some way you have to map it to business events, because then you can work on it. You can work on it in your stream, in your Scala code. And you can actually work on it in a type-safe way. So that's the first step that you will do. You actually map them to, in this case, car locations. Yeah? So I have not raw data now in my stream set, but actually a collection of car locations, GPS data. Then we're going to apply the business rules. Remember, in our first diagram, we had this nice business rule engine on the top, which you probably should be calling here, but in this case, I just have a very simple filter, and I filter on the location that is saying, okay, only take the events within this latitude and this longitude, and this square of the country, so to say. So a map, a filter, and and in the latest time we said you want actually to store the events on a Kafka cluster to be able to replay all the events that have been doing in the past, and to provide data scientists with a way to train their own models. And I work on the RAD method here. Actually, in this case, you can choose what kind of mechanism of Spark you want to use for doing things. You can choose a data frame or a data set. And in the next release, or actually it's in the current release already, there's also structured streaming, but that's still an alpha release, so I'm not going to talk too much about that. But it's also a way to go through your event stream and, for example, select a sliding window or select a duration for your stream. In this case, I have a very basic mechanism, namely the RAD. In each RAD, I'm just going to insert my car location into my Cassandra cluster. All right, and the last part is actually doing the fun stuff. Once we have those kind of events, and we have mapped them and filtered them and stored them, we actually want to predict what car park is now the most relevant for us at this moment. And I have too little time to explain everything about this, but the interesting part is, let's see, this one, the score prediction, of course, and assuming we already have a model here somewhere loaded from our cluster of our learning environment, a Spark machine learning model, like a regression model, we actually predict, and we have to translate our data to a vector first. We can get the score by just calling the predict function of our model in this way. And in the last step again, we have a new score and we update it again to the Cassandra cluster. And then it's ready to be there to be used for the API that's calling it. Now, in batch, actually, it's what you will see if you look at this. It's different, but it's actually, yeah, surprisingly similar code, right? So, while in the streaming use case we use the events coming in from a Kafka bus. So obviously we have to connect to Kafka and then process all the events, and then after that do a loop and on all the car parks that are relevant. In this case we don't have that first part, we just load data directly from HDFS, and we have a feature set of car parks already available. So the code is slightly shorter and simpler, but in this case this is getting the car park from the text file of HDFS and predicting the score, updating the features, and actually calculating how many cars are in the neighborhood is exactly the same code as we had before in our stream. So this is really combining stream and batch in the same way with the same code working on the same data, namely the feature set. And for data scientists among us, I always like to work with Zeppelin as a tool. That is actually a front-end tool running in your browser, which you can just load Spark code in, and which is connected to your Spark cluster on the back end. So if you give this to data scientists, they will be very happy because they can write Python code or Scala code and have their own models trained, you loading data, training the model, and doing test runs, and then exporting and storing the data to your local machine or to a file system, ready to be picked up again by your streaming and batch combined solution, which we just talked about. Okay, I get to the summary with 4 seconds left, so that's nearly finished. We talked about Internet of Things, a new, business model for doing lots of things with new data, all connected data sources. Why is there an Internet of Things? Well, because the hardware prices are dropping, right? I don't know if I explained that right. Why we're even talking about it. Yes, it gives us some nice use cases, but also because it's now possible. Right? If the price of a network connection, a Wi-Fi connection, and a CPU and some storage space is dropping below €1 altogether, yeah, then it's really interesting to actually connect all those kind of devices. But it gives us new challenges, right? We have even more data to work on. We have even larger security problems to face. So we really have to think about doing things more efficiently, faster, in memory, distributed. Well, in comes Spark, of course. That's a very nice solution to deal with this kind of things. There are several reference architectures with different names: Lambda, Omega, Kappa, you name it. I just keep calling it Lambda, but it's actually the basic principle there is combining those two in a system where you actually you have the challenge of combining them as early as possible in your process, because that is the most efficient for your code reuse and your data reuse. And finally, I talked about the SMAC stack, the technology stack that could be used for this. Cassandra, Kafka, Spark, of course, and the M is for Mesos, and the A is for Akka, all, again, distributed, scalable systems that can be used in this kind of scenarios. Okay, that's it. I'm slightly over time, but I hope you enjoyed it. Thank you.